In the last video, we had an introduction to the concept of vectors. A vector is a mathematical quantity that has both a magnitude and a direction. We represent vectors with arrows graphically, and we'll use this component notation to represent them. Two vectors are the same if they have the same magnitude and direction, so we can have lots of different vectors that are all the same even though they're in different positions in the plane or in 3D space. The vector that starts at the origin is called the position vector, and we looked at two basic operations of vectors: vector addition and scalar multiplication. To add vectors in terms of a picture, we simply take two vectors and put the terminal point of one at the initial point of the other, and then the overall vector that we get is the sum. Scalar multiplication, we just take a scalar, just a number, and we multiply it by all the components of the vector, and that gives us a scaled vector. One very important concept here is that two vectors are parallel if one is a scalar multiple of the other. The length can be computed using this formula here, which is an analogy to the distance formula in 3 dimensions. A unit vector is a vector of length 1, and we can always find a unit vector parallel to a given vector if we just take the original vector and divide all the components by the magnitude of that vector. An alternate notation that we'll sometimes use is this ijk notation with the standard basis vectors. I is the vector 1, 0, 0, j, 0, 1, 0, and k, 0, 0, 1. So we can represent vectors either in component form or with the ijk notation. Now let's work through some examples. For example 1, we want to write the vector with the initial point at 3, 1, negative 1, and a terminal point at negative 2, 0, 4 in component form. The way to get a vector if we're given the starting point and the ending point is to take the terminal minus the initial. So for example 1, we're going to find the vector by taking the terminal minus the initial. My notation is going to be a little bit sloppy here. This really isn't great notation that I'm going to use, but I think it helps to get the point across, so I'm going to write it down anyway. I'll take the terminal point, negative 2, 0, 4. This is a point, it's not a vector, and I'm going to subtract off the components from the initial point, 3, 1, negative 1. And I'm going to subtract these just coordinate by coordinate. So I start with negative 2 minus 3, and now this is going to be a vector. Negative 2 minus 3 is negative 5. 0 minus 1, negative 1. 4 minus negative 1 is 4 plus 1, which is 5. So I get this vector, negative 5, negative 1, positive 5. This is the vector that starts at negative 2, 0, 4 and ends at 3, 1, negative 1. Now let's find the length, or the magnitude of this vector. To find the magnitude of negative 5, negative 1, 5, we take the square root of negative 5 squared, that's 25, plus negative 1 squared, that's 1, plus 5 squared, 25 again. This is the square root of 51. That is the magnitude of this vector. Let's take a look at how to draw vectors in GeoGebra. In order to plot a vector in GeoGebra, you first have to type in the word vector. So if you start typing in the word, the command will pop up, and we want a vector where we now input the values of the components. So we just enter this like we'd enter a normal point, negative 5, negative 1, 5. So there we have our vector, negative 5, negative 1, 5. By default, GeoGebra graphs this as a position vector, which means that the initial point is at the origin. But GeoGebra can actually graph vectors between any 2 points that we want. In fact, in the problem that we have an initial point of 3, 1, negative 1, and then a terminal point of negative 2, 0, 4. So we can graph that exact vector at those points in GeoGebra. We do that by entering vector, and we take this second option here for a start point and end point. The initial point is 3, 1, negative 1, and the endpoint is negative 2, 0, 4. So there we have the original vector. Notice that the position vector, the negative 5, negative 1, 5, is parallel to that vector. They're both the same vector, just drawn at different locations. Also, notice that GeoGebra gives us the components of the vector. It just gave us this negative 5, negative 1, 5, which we had solved from the problem. Let's solve example 2. Our goal for this problem is really just to be comfortable with the basic vector operations and to be able to visualize what we get. So we have a vector A, which is 1, 3, a vector B, which is negative 2, 4. Let's go ahead and graph those vectors first. Starting with the vector A, we move 1 in the x direction and up 3 in the y direction to arrive at this point. So here's the vector A drawn as a position vector. We could really start anywhere we wanted. I could have started, say, here, and as long as I go 1 in the x direction and up 3 in the y direction, well, this would get me to this point here. That's the same vector, just drawn in a different spot, but we'll just stick to drawing the position vectors here. So there's the vector A. The vector B is -2, 4. So if we want to draw B, we go -2 in the x direction and up 4 in the y direction. So vector B would look something like this. Let's find the sum of these two vectors. How do we add two vectors? We simply add their components. So 1, 3 plus -2, 4. I add the x components together. 1 plus -2, that would be -1. And then 3 plus 4 is 7. So I get the sum of -1, 7. -1, 7 is this vector here. Go -1 in the x direction, and then go up 1, 2, 3, 4, 5, 6, 7 in the y direction, and we get there. That's the vector which is their sum. So here's the vector A plus B. We can think of getting there graphically by taking the vector B, placing the initial point of B at the terminal point of A, and then just graphing the vector B. So we go over -2 in the x direction, and then up 4 in the y direction, and there we have the sum graphically. So we want to understand how to get the sum analytically by just adding the components, and then what the sum looks like in terms of the graph. Let's find 2a and then -b. 2a is just multiplying all the components by 2. So 2a is simply 2, 6. If we graph the vector 2a, it's in the same direction as a, it's just twice as long. So it would look like that. There's the vector 2, 6. We're just doubling the magnitude of a. -b, we just multiply all the components of the vector b by -1. So -b is just 2, -4. If we graph -b, then we go 2 in the positive x direction, down 4, and we just have the vector b completely flipped around backwards. To find a minus b, we just take the components of a and subtract the components of b. So a minus b, we'll take the x component 1 minus -2, that will give us 3, and then 3 minus 4, that will give us -1. So vector subtraction is just, instead of adding the different components, we subtract. 1 minus -2, 3, 3 minus 4, -1. So there's the difference between the two vectors. Let's find magnitudes. The magnitude for the vector a, we use the magnitude formula. So the magnitude of a is the square root of 1 squared plus 3 squared. 3 squared is 9, 1 squared is 1. We have the square root of 10. That's the magnitude of a. B, same sort of thing. We take the square root of the first component, -2 squared. -2 squared is 4, plus 4 squared, that's 16. So I'm just squaring my different components. Add them together, take the square root. We have the square root of 20. That's the magnitude of vector b. How about part E of this problem? Here's a concept that we really want to be familiar with. How do we find the unit vector in the direction of a given vector? Well, the formula is to take the given vector and divide by its magnitude. So we're going to take the vector a and divide by the magnitude of a. Well, the vector a is 1, 3, and we just found the magnitude. It's square root of 10. So I'm going to divide each component by the square root of 10, and the unit vector in the same direction as a is just 1 divided by square root of 10, 3 divided by square root of 10. If we find the magnitude of this vector, we'll discover that that magnitude is 1. We know that it's parallel to the original vector a because it's a scalar multiple away from a. So here is the unit vector in the direction of the vector a. Finally, let's answer part F here. If the initial point of b is not at the origin, if we don't have a position vector, if the initial point is at -2, -2, where's the terminal point? Well, we're just going to simply start at -2, -2, which is right here. And we're going to go in the direction of b. So we go -2 in the x direction, and then up 4 in the y direction. 1, 2, 3, 4. We reach this point here. So here's the vector b, just not drawn as a position vector. The terminal point here is the point -1, 2, 3, 4 in the x direction, and 1, 2 in the y direction. So the terminal point here would be -4, 2. Let's take a look at how to plot two-dimensional vectors, and for this we're going to use Desmos. Unfortunately, Desmos doesn't really have a pretty way to draw vectors with the arrows and everything, but there is a way to generate vectors. So we want to first graph the vector a, which is 1, 3. I'm just going to graph the point 1, 3, and then add a t afterwards, and it instantly changes it to, actually it's a parametric equation, t comma 3t, where t ranges from 0 to 1, but really that just gives us the vector that we want, the vector 1, 3. So if we want to, we can call this a, and then b is the vector negative 2, 4. So we can type in just the point negative 2, 4, and then write t afterwards. There's the vector negative 2, 4. Desmos draws these as position vectors by default, but we can change that by just adding a point. So if I take b and just, well, I'll add the point a, 1, 3, and then we see that we get the vector b just moved so that the initial point of b is at the terminal point of a. And if we add a and b together, we see that we get the sum of negative 1 comma 7, which we expected from adding them together. If we think about the last part of the question that we answered, where we had the initial point at negative 2, we can simply add the point negative 2 to the vector b, and there we have the vector b starting at negative 2, so we can see there that our terminal point is negative 4, 2. So it's fairly simple to draw two-dimensional vectors using Desmos. Take a look at example 3. Here we're given a vector, negative 2, 6, negative 4, and we want to know which of the following vectors will be parallel to the one that we're given. How do we find out whether or not two vectors are parallel? Well, they're parallel as long as one is a scalar multiple of the other. So when we're trying to check these different vectors that we're given, we want to see if we can multiply the original vector by some number to obtain the different options. So take a look at letter A here. Can we obtain letter A by multiplying the original vector by a scalar? Well, I have negative 2 as the x component, and I have positive 2 here. So I just have to multiply by negative 1. But if I multiply the middle component by negative 1, I get negative 6. This one's not going to work. So letter A, that is not a scalar multiple of negative 2, 6, negative 4. How about letter B? Once again, we have an x component of 2, so we'd have to multiply the original vector by negative 1 to get to the x component of 2. If we multiply this original vector by negative 1, we have positive 2, negative 6, positive 4. Aha, that's exactly what we've got here. So this vector is parallel to the given vector. How about letter C? Well, to go from negative 2 to negative 6, we'd have to multiply by 3. Negative 2 times 3, negative 6. 6 times 3, 18. Negative 4 times 3, negative 12. Letter C also works. It's a scalar multiple of 3 times the original vector. So this is another vector that's parallel to the given one. How about letter D? Notice that we've really just rearranged the order of the components. Instead of having negative 2, 6, negative 4, we have negative 4, 6, negative 2. Does rearranging the order give us a parallel vector? Well, let's check it out. I need to have a scalar that I can multiply the original vector by to get to this new one. To go from negative 2 to negative 4, I'd have to multiply by 2. But if I multiply 6 by 2, I don't get 6, I get 12. This vector does not work. So letter D is not parallel to the original vector. How about letter E? Can I multiply the original vector by a scalar to get to E? Well, to go from negative 2 to 1, I would have to divide by negative 2, or multiply by negative 1/2. Okay, if I divide by negative 2, then for the 6, divide by negative 2, I get negative 3. Divide negative 4 by negative 2, oh, I get positive 2. This vector also works. It's negative 1/2 times the original vector. So it's parallel to the original vector. Finally, how about negative 4, 8, negative 8? We'd have to multiply the x component by 2 to get to the negative 4, but 2 times 6 is not 8, so letter F, this vector is not parallel. There's not a constant that we can multiply the original vector by to get to this vector here. Let's use GeoGebra to visualize these parallel vectors. Our original vector is negative 2, 6, negative 4. There it is. It's dashed because it's below the xy plane. So there's the original vector. And we found that the vector 2, negative 6, positive 4 is just the negative, so it's the same exact length, but in the completely opposite direction. There it is. Those vectors are parallel. The second one just goes in the completely opposite direction. If we multiply the original vector by 3, then we get this vector here, which is quite a bit longer. So there's another parallel vector. And then finally, if we divide the original vector by 2, then we get a vector that's half as long, which would be this one, right? The brown one there. So all of these vectors are parallel to the original vector 2, 6, negative 4. We can visualize this in GeoGebra.